Welcome back to our lectures. Today we are going to talk about real-time systems. I think you have an impression what is real-time system. Maybe you will think real-time means as fast as possible. That's not true. Real-time systems has to be fast, is sometimes true, but not as fast as possible. There is a limit in both directions. First, I'm going to show you what I mean. When we want, for example, to take this picture, this is a real-time system. So you cannot come too early and you cannot come too late. You have a time window when you can take these pictures. Else the picture will not be what you want to see. So let's correct. Does it has to be fast? And the faster the better? No. It has to be fast? Yes, maybe, but not the faster the better. It has to be at the right time. Too late is bad and too early is bad. So we are talking not from a time point, we are talking from a time window. And this time window has two parameters. Latest time, latest possible time, later than that is bad. And earliest time, earlier than that is bad. And how it works. First, we had to get prepared and then take the action to the right time point. So, like this. You had to go very fast until the next red traffic light and then stop and be ready for the next action. Like this. You have to get ready, so you go as fast as possible as you can until this point, and then you wait. When the green light comes, then everything is ready and you can proceed. Now let's compare a real-time operating system and a normal operating system. They are optimized for different things. A real-time operating system is what we need here. They are optimized to reach the time window, not to utilize the CPU as good as possible. Normal operating systems, they don't have something like time windows. They are optimized to use the CPU as good as possible. So everything the CPU is free, you are going to execute the next task to keep the CPU active. So the processor is going to be utilized as good as possible. Here not. In real-time operating system, you have to wait until the real time. So you have to be ready before the time arrives, and then you have to wait. And when time arrives, then you go. So a lot of time you spend just waiting. So much waiting, and therefore you have a bad CPU utilization. Okay. Here I have an example about this time window. That is the best example I know in a circus. Here in the circus we have these flying trapezios. You know, two persons are flying here, one jumps and hopes the other will be there at the right time point where he can catch him. If not, he will fall down. Let me show you an example and try to see how it works and try to see the size of this time window. How much earlier or how much later he can arrive. For example, oops, just a second. I have to correct something and make it again. Okay, here we are flying again, and you can see it has to jump at the right time, and perfect, it works. And going back, the same situation, it has to wait or to be ready at the right point. And now maybe you got an impression how much time, how the size of the time window, how much time can it be earlier or late. Let's see it in slow motion. Just a second. Now the same thing in slow motion. Let me see. The speed is a third of the normal speed. So you can estimate how much earlier or how much later it can be. But the best is when flying back. And try to see the size of the time window. I estimate it is about 1 second. Here is the trapezium, you see, he is flying and perfect. Well, obviously, this is a very experienced man. But it doesn't have to be so perfect. It can be a little bit late, earlier on or later. He can correct with the position of the hands. This is the possibility. So he has to look and control. And now let's see the effect of a timing error. This is in the school for trapeze flyers. And now, flying back. So, failure. Maybe an accident. So, you can estimate what is the size of the time window and try to see he was too late or too early. Now, I'm going to play the same in slow motion and try to see, just a second. Now inside motion, here you can see the trapeze. Can you see? The trapeze is gone and then he is falling down. So, too early or too late? Let me know. Here comes the trapezium. Can you see? Here is it. And no chance. Okay. What is your impression? Too early or too late? By the way, this we are going to give you some questions which you shall answer and present to your local coordinator. This is one of the questions. This trapeze flyer with the timing error was too early or too late? And how much? Okay, and now let's see another case of maybe timing error or something different. Try to identify what is it. Okay, now she's flying. What was the error? Was it a timing error or something else? If timing error, too early or too late? Let's see in slow motion and then try to identify what was the error. Okay, what is your opinion? Was it a timing error? I don't think so. The time was good. Both were at the same position at the same time, but the position of the arm, it was wrong. It was too far away. Therefore, we have two possibilities to make a mistake. Timing error and reaction error. Both are wrong. Okay, or possibility to be wrong. And we are talking about time windows. We define the time window with two parameters, I said before, the earliest possible time and the latest possible time. And the time is going in this direction. So what you have to try is to be here in the red area. We have two, we have two types, at least two types of real-time systems. We have time critical, the same like hard real-time, and we have soft real-time or time sensitive. The difference is if we have a real-time system or time critical, you have to be inside of the window. If you are a little bit outside of the window, you have a total failure. So an accident or the system had failed, nothing to repair, it's gone. An example is, let's assume you have to take a train and the train will depart at 12:37 and it will be exact. At this time, they close the door and the train goes. If you are not inside, everything is gone. So it makes no difference if you come 1 second too late or if you don't come. In any case, the result is the same, you miss the train. So that is hard real time. When they begin closing the door, no chance anymore. 1 second difference, everything is lost. So if you come 1 second, 1 minute, or 1 hour later, it's the same. Everything is lost. Okay. The other case is time sensitive or soft real time. If you are outside of the time window, not everything is lost. This is only getting worse and worse and worse. For example, you have an appointment with your friend or your girlfriend, and you say, I will be there at 12. And you come 1 hour later. Not everything is lost, but the friend will be maybe not so happy about this. So if you are coming later and later, you are losing points. So it's getting worse. Another example, let's assume the homework. If I say, you have to deliver the homework until tomorrow at 12, no more. At 12, I'm going to close the server. And the server is not going to accept any exercise anymore. Then it's hard real time. If you are 1 second too late, everything is lost. Exactly the same if you didn't do the homework. This case is, I will say, until 12, you get the best points. For every hour later, I will take 1 point away. So you can come 1 second later, or 1 hour later, and so on later. At one point, you have lost everything, but it's not abrupt. It's going only worse. And that can be in both directions. And then we have the other case. These are tasks which are not time sensitive. So you can come whenever you want. I can say, for example, when you want to make the exam, come whenever you want, just tell me and we do the exam. So there is no time restrictions. The piston seal can be damaged. So to keep the pressure inside of the colvent between the piston and the upper part, you have here some seal to avoid the air to go from this. But this has a limit. If the pressure here is higher than it can support, it will break. And this could be the case. And then in both cases, we have a motor damage. Therefore, if we are too early, we have a hard real time. We are damaging the motor. If we are too late, then we are just losing effectivity and the burning will be not so perfect. So here you can see this is not symmetric, the cost function in both cases. This is only a few examples. And now let's take an example, the consequences of too early or too late. Let's take an example for aerospace. Let's assume you have a rocket. This rocket is in orbit, so it's flying around the Earth or the planet with the perfect speed to be in orbit. So if we change this speed, for example, with thrust, with ignition, then we can brake, decelerate, we lose speed, and then we can fall down. Or if we accelerate in the direction of the movement, then we are going to get more energy, and then we can get in higher orbit. But let's assume we are moving in this direction. So after ignition, we are going to lose speed, and if we lose speed, we fall down. Okay, so depending where we want to land, then we have to compute when shall we begin with ignition, when shall we ignite. If we are exact at the perfect time, then we are going to be at this position, and then if we ignite too early, then we begin braking here, and then we can fall down here, for example. If we are too late, maybe here, then we are going to fall at this position. So a timing error at this position is not so bad. The only consequence is we are not going to be exactly at the time, at the point where we wanted to land. It can be a few kilometers too early or too late. Well, depending where you want to land, on the Earth or on Mars or something like this, it could be worse or better. It doesn't matter. Okay, so you can see what will be the consequence of ignition too early or too late. And this is not measured. When to ignite is compute on the Earth. So we make a computation where we want to land, and then we make a time program and say at this time point, it shall be at this position, so please ignite. So there is no sensor which says I am at the right position, now I shall ignite. It's everything pre-computed and is controlled by time. And now let's assume the other point. We are landing. When landing, we have to brake. And to brake, we are going to use the same ignition, the same thrust system. So we are losing speed. And if we do everything perfect, when we reach the ground, the speed shall be 0. Deactivate the ignition, the thrusters, and then we stay on ground. Everything perfect. And now it could be pre-compiled or pre-computed before, and everything is function of time. And then what will be the consequence if we stop too early or too late? If we are going down and we stop too early, then we are going to fall a few meters and maybe we have a crash. If we are too late, then at this point it will not break, it will continue rising again, then we stop and then fall down and we have a crash again. So you can see the consequences of a timing error here are very different than the consequences of a timing error here. So everything controlled by time. Okay, now we have seen what is real time. Now let's talk about time. What is time is a difficult question. We don't know what is time, but it doesn't matter. We don't know. We don't need to know what is time. We just need to know how to use time, how to measure time. We have 4 methods for using time. The first method is what we use normally. This is a linear time. We begin counting the time at some time point. It can be different things. It can be, for example, when you turn on the computer. It can be something later when you start the ignition and start flying. It can be earlier at a fixed time point. It doesn't matter, but we have a linear time. It begins 0 at one time, and it continues increasing, going until end of time, which can be very, very far away. Maybe 100 years in the future, I don't know, when we have an overflow in time. And every time point, every value comes only once. And this is what we are using in our real-time operating system. The time continues growing and growing linearly from 0 to until the end, until you turn the machine off. The other is using a cycle time. So this time begins at the beginning of a cycle. It goes around the cycle, and when it concludes the cycle, it begins from 0 again. And all time points are relative to the beginning of the last cycle. In this case, all time points are relative to the 0. For example, when you started the computer, when you started the rocket, or whenever you have. But here, you repeat the 0 always again and again every time you begin a new cycle. So it doesn't matter how many cycles you have done. Like controlling the piston, the motor. When you are controlling the motor, it doesn't matter how many cycles you have done, millions of millions, but all control is relative to the beginning of this cycle, when the piston is going up and when the piston is going down. Okay, another way to use the time or to measure the time are time counters, countdown. So, and this time, you set when shall be executed something, and you count down from this time point, let's say 10 minutes going to down, and when you reach 0, you have to perform one action, single shot, and it is done. Another way to control, to use the time is the right time point, only one point. For example, when shall we take these pictures? In this case, we don't have a counter, we have an external signal. We don't have a time counting system, we have a reactive system. So something is going to occur outside of the system, then you get a signal, and then you have to handle at once, very fast. So this is without time counting, just a reactive system, reacting to a signal. I hope it's clear. Now let's talk how to recognize the right time to handle, to execute something. Let's assume this very simple example. We have some boxes which are moving here, and we shall classify or sort these boxes in this container. We have one container per color. We have here a camera, and the camera is just looking at the color, and then we shall compute when shall we activate different arms here. For each container we have an arm, and this arm is just going to push the box, so the box is going to fall down in the corresponding container. Okay, now you will know which information we need to know when shall we activate the corresponding arm. SAC. Do you know? I think you will see. First, we need the speed. Which speed is moving the boxes? They have a constant speed. And then the distance. But which distance? The distance under this point, or the distance under the position of the arm which shall push the corresponding box. And we have, in this case, 1, 2, 3, 4, 5, 6 different arms. So we have 6 different distances. And the computation is not really difficult. We recognize that. We know the color. Then we know the distance until this position. And then we can compute the time when this box is going to be here. And then push. Now we have two options. Maybe we have a time schedule, a complex systems, where we control all these arms. And this will be difficult because, for example, we have the blue box, and after the red box, the arm shall be activated here, and then we have the blue box. The blue box comes later, but this arm shall be activated earlier. So we have to sort the time points where to activate each arm. Another way to make this is what we do in control systems, in real-time control system, is we create several threads. And each thread, or small application, let's say, is responsible only for one single thing. And with this concluded, the thread can conclude or begin again with the next task. So the most simple thing to program is to have different threads. Each thread is going to handle only one box. So when we recognize a box, we start a thread, we compute when the corresponding arm shall be activated, and the thread waits. Only waits until the time is come, and then he knows which arm to activate, and then push the box. And so we are going to have one thread per box. Much more simple to program and to implement. And this is one of the reasons why real-time control systems are multi-threading, or applications, let's say thread or applications, many applications are running at the same time. There is a difference between normal applications, which you know from the telephones, from the smartphones, and from threads. On the applications, normally one application runs only one. Here, every 10 thread can be the same applications, but a different activation of the same application. For example, the application is always the same, wait so long, and push one arm. And we can have, in this case, 1, 2, 3, 4, 6 of these threads running at the same time on all the same application. Okay, now another important thing, how to recognize the right time point to handle, to do something. We have 4 alternatives, or even 5, but 5 we are going to come later. The first one, the most simple way, is we have used a sensor which reacts to an external event. And this sensor says now, do it now. So we have no time counting, we have only this external signal, this says do it now, and then we have to do it as soon as possible. So no one of these has a counter, he has to wait until this signal and then start running. This is what we call a reactive system. It reacts to an external event. Another is pre-computed time points. This is a typical example with launchers, with rockets. When the rocket is going to perform different actions, it's all pre-programmed. We have a schedule at what time shall do what things. For example, the separation of the boosters. You will think the booster shall push the rocket until they are empty, and then when they are empty, they will be separate. But it is not so. On ground, they have computed when they will be empty. So there is no sensor which says they are burned out, they are empty. We have computed when it shall be empty, and then we wait until this point, and then we have the separation of the booster. So everything is pre-computed, and it knows only the time point where to execute which action. So it's a time control system. Exactly the same with ignition. There is a time schedule when says when to ignite each system. So every time is time control, pre-computed. Okay, then we have this other system. We have a sensor, like this before, and we know this time delay. And then we start a countdown, and then we take the action, like this. And the other is something in between this, and this, but this is a combination of reactive system and time counting. So, for example, here we shoot ourselves this bullet. We don't have a sensor which says we have shoot. The computer has the control and it shoots, and then the computer shall know after shooting I have so many milliseconds to take these pictures. So it's a trigger system. We trigger ourselves, wait, and then take the next action. And this, we get a signal from outside, and then we set and count down. Okay, I hope this is clear. That is the third question which you shall answer. Tell me what are these 4 ways to recognize the right time point. Okay, now let's take a look to the 5th. I said we have 5. And 5 is all of this, but cyclic. As you can see, this is a single shot. Everyone will be activated only once. But there is another possibility, all of this, but it will be repeated. For example, the control of a motor. It will be repeated. So all of this, but cyclic. Okay, now, how fast shall it be? We know already how to recognize the right time point to handle or time window, it will be better. But let's consider, does it has to be very fast? Do we have short time or we have long time? And we have both of them. Some systems have a very short time to react. Some systems have a long time to react. Let's assume this a cyclic system. And then let's consider the size of this cycle. For example, in this control of our automotor, the cycle will be maybe 10 milliseconds. We can have shorter or longer cycle. I have here some examples of very long cycles and very short cycles. For example, a very long cycle are the bank applications. One per month, they shall, they shall generate a status report on every account. And this is done only once per month. So the cycle is 30 days, a very long cycle. And then you have several hours. You don't have to be exact at this time point. We have the night to make these computations. Something a little bit faster is, for example, the alarm clock you use every morning. So every morning you would like to wake up and then you use an alarm clock. And this alarm clock has a period of 24 hours. So every day, every 24 hours, we are going to do the same operation. Ring or something like this. Okay. Our next example, getting a little bit faster, is traffic light control. In this case, you have different phases of colors, and these phases are going to be repeated in minutes or seconds. Okay. Our next example, getting a little bit faster, is, for example, satellite control. Satellite control, actually, they are not very fast. 500 milliseconds per control is enough. So we have to control the satellite only 2 times per second. And maybe you will say, why so slow? But satellites are moving very slow. If we take the rotations of the satellite, they are rotating, but they are rotating really, really slow. So this period is enough. Something faster, for example, aeroplanes, they are moving faster, and therefore we need a faster control cycle. Typical for controlling aeroplanes of turbines of aeroplanes is about 100 milliseconds per cycle. So every 100 milliseconds we repeat the same controlling action. Then the automotor, it is faster. We need a cycle of about 10 milliseconds. So we are getting faster from days to milliseconds. Quadrocopter control. Oh, here I forgot to show you. I'm going to show you in few seconds. Quadrocopter control, we have 4 motors, and we have to compute the rotation speed in all directions. And if we want to keep this attitude, and we are rotating in this direction, then we have to add more power to this motor to compensate this and keep the quadrocopter to these positions. Exactly the same, if we are keeping in this direction, then we shall add more power to this motor to keep this direction. And this is something it has to be done with a period of 3 to 4 milliseconds. If we are too late or too early, we can have an accident. I'm going to show you an example in few seconds. Okay. Then we have the control of robot sensors. These are the joints or moving arms of motors. And if we have some movement, then we shall have a control somehow fast. And the launch, the vector launch, the vector shoot of rockets, it's about 1 milliseconds, the cycle time. Then we have missiles. The missiles are flying very fast and they have to be very agile. Then we have to control about 100 microseconds. This is 10,000 times per second, so a very short time period. And the fastest I know is the control of cyclotrons. Maybe you know what is a cyclotron. In cyclotron, they are accelerating electrons, or maybe heavy ions, to almost the speed of light. So it is really fast. We have magnets, and with these magnets, we keep the electrons flying around one path. And they have to be controlled in microseconds to nanoseconds. Hence, the electrons will go in other direction and crash on the sides of the tube of the cyclotron. And I wanted to show what is the case if we have a timing error. from quadrocopter. We are building quadrocopters and therefore we can show. Let me see, this is an example, one quadrocopter from us. And you can see we have these 4 rotors, 4 motors with 4 propellers, and then we are flying. And I said before, we have to measure the rotation speed, and to keep the desired attitude, we have to control these motors with a timing of 4 milliseconds. So let's see how we are flying. It's flying okay. And at this time point, we have a timing failure, and this is the result of a timing failure, a crash. And we know why, because in our quadrocopters, we have a logbook, a black box, or flight recorder, and we are recording when are we sending signals, which signal to each motor. And in this case, we lost some control signals to this motor. It is cyclic. The next signal came 10 milliseconds later, but 10 milliseconds was already too late. The quadrocopter was already too far away from the original plane, and it was not possible to control anymore, and then we had the accident. Let's take a look in slow motion. Again, the same thing in slow motion. So you can see, this is the motor. We lost one message, only one message, and this was enough for the crash. The difference was less than 10 milliseconds, but 10 milliseconds was really too long to keep a stable flight. So quadrocopters are very unstable systems. By the way, if we are talking about this, I have here a very interesting example of time window. I'm going to show it now. The difference between life or death is maybe only 1 second. Take a look to this movie and see what is the difference between staying alive or dying. Did you see? Did you see the motorcycle? Let's do it in slow motion. Which speed? I don't know. But let's take a look. Here he comes. Then we have the accident here. The space was very short in both directions. So for these persons, the difference to die or stay alive was less than 1 second. Maybe if he had come half second later, he died on one direction, or half second later, he died on the other direction. So it's a very nice example of a very critical time window. He was exactly inside of the time window to survive this accident. Okay, but now let's come back. This is not what I wanted to show. We were talking about the cycle time. Okay, so you can see from very long to very short cycle time. And if we want to control these machines, we shall think which resources or which instruments can we use. You will see to control this, you can use any operating system. So it's not so critical. To control this, you cannot use the same means like this. Okay, I have here a diagram. What can you use for different time periods? For example, for these time periods, days or hours, you can use a normal operating system. So here, 1 minute earlier or 1 minute later, it makes no difference. So any operating system will be able to control an alarm clock or a bank application. When we are talking about seconds, for example, satellite control, traffic line control will be normal operating system too. But in this case, we are talking about less than 1 second. Then a normal operating system will not be able to execute with the precision we need. We shall use a real-time operating system. And using real-time operating system, we can go as fast as 4 or maybe 3 or 2 milliseconds. When we have to control something which is faster than 1 milliseconds, then we cannot use operating system anymore. We have to have a very simple solution, and this is what we call the big loop. So in real-time operating system, we can have many threads running at the same time, which makes everything much more simple to program. Do you remember the example of the box which has to be classified in different containers? We saw the most simple solution is to have 1 thread per box. Okay, for that you need an operating system. But here, You cannot have an operating system anymore. A control of 1 milliseconds is too much, too fast for your operating system. So you have to have a big loop. This is a single program, only a program which is doing always the same. A very simple operation, but very fast. Okay, this is a big loop operation. And with this, using big loop, no operating system, you can be maybe as fast as 100 microseconds. But then it's the end of software. If you have to control something faster than 100 or maybe 15 microseconds, for example, this cyclotron, where you had microseconds to nanoseconds, no chance to do it nowadays with software. So you have to have dedicated hardware. And the cost here is getting higher because you have to have dedicated hardware. You cannot have a single processor doing many different things. Okay, this is one parameter, the cycle time. Another parameter is the jitter. Let's assume a cyclic system. Okay, a cyclic system shall repeat every cycle time. I don't know, let's say 100 milliseconds. Every 100 milliseconds it shall do something, for example, motor control. And the period is 100 milliseconds, and in the middle it shall do something, 50 milliseconds, let's say. And the question is, how exact will I touch this 50 milliseconds point? It will not be always the same. If we are using hardware or software, sometimes it will be a little bit later, sometimes it will be a little bit earlier. And this is what we call the jitter of the delay. Okay, if we are using hardware, dedicated hardware, then our jitter is going to be very low because we have transistors which are doing only this, and the jitter of transistor is picoseconds. So using dedicated hardware, you have a jitter of much less than 1 microsecond. So the time point will be very exact. The next, if you use CPU and software, the fastest reaction you can have is using interrupts. Using interrupts, you have an interrupt time of about 3 milliseconds, up to 10 milliseconds, according to the processor you are using. So you are going to have a jitter of about 10 milliseconds in the front or in the back. So the time are not always be the same, sometimes here, sometimes here, and you are going to have these vibrations, this jitter. Using a big loop, you have a jitter of about 1 millisecond. This is shown almost 1,000 times bigger. Because when you react, you are in a loop. Maybe the signal which you shall handle is here, but your software is here, and you have to wait until you reach this position. And then you can see, I have to do something. I have to handle something. And the size of the loop can be 1 millisecond. So if you are very far away, it will take longer. If you are very close to the position where you have to react, then it will be faster. So we have this vibration, this jitter of maybe 1 millisecond. Using a real-time operating systems, we are going to have a bigger jitter, 3 to 10 milliseconds. Because normally, the reaction of a real-time operating system is a thread switch. One thread is doing something, then this thread has to be interrupted, the CPU will be taking him away, and you have to activate another thread which is going to handle this action which you have to execute now. And this thread switch costed between 3 and 10 milliseconds, according to the speed of the processor and complexity of the processor. So you are going to have this jitter up to 10 milliseconds. So you can see how this jitter is growing. And using normal operating system, for example, Linux systems, you can have a jitter of about 100 milliseconds, because this is the time scheduling time of Linux. Every not faster than 10 milliseconds, 10 times per second, they are changing thread. They can react to interrupts much more faster, but if you are using thread vexen or task vexen, you can say you are going to have inaccuracy or jitter of 100 milliseconds. And the worst case is the Windows family. They are absolutely not optimized for these time systems, so the reaction can be up to seconds. So you can wait up to 1 second until you see the reaction. So according to the precision of your system, you have to take the decision how complex or what you shall use. Okay, and these are the two parameters which you shall consider: the time period and the jitter which you can tolerate. Okay? Now, time measurement. And now let's see how to measure the time or how to count the time. Surely you know this method which we use normally. Here you can see it. From the top, you can see we use years. Sometimes the year had 365, sometimes 366 days. Then we have months, 12 months. And months, sometimes they have 28, sometimes 29, sometimes 30, and sometimes 31 days. And then we have days with 24 hours, then 60 minutes, 60 seconds, and from there, below seconds, we got in that decimal systems, milliseconds, microseconds, nanoseconds, femtoseconds, and so on. So as you see, we are having many different types to count, and using this method is really difficult to count to make the time difference between two time points or to increment the time counter by some other time counter. So this is a very terrible method and we never use this. What we use is a seconds counter. So you can see here, and we can count the seconds from different time points. Typically, for control applications, we count the seconds from boot time, when we start the computer. Or for cyclic systems, we count the seconds from beginning of the cycle. And then we have UTC time, and then we count the seconds from 1st of January, year 2000 at 0 UTC 00. Well, and when I mean seconds, I mean the seconds and fractions of seconds, milliseconds up to like picoseconds according to the accuracy of your clock. Okay, but there is something more than that. We have leap seconds. Do you know the difference between this year with 365 and 366 days? Is a leap year. So we are adding 1 day to stay synchronous with the Earth rotation around the sun. To stay synchronous with the Earth rotation on its own axis, to point at the same time to the same star or to the same position of the sun, we have to do something similar because the rotation of the Earth is not very constant. So we have to add seconds. And this is what we call leap seconds, because the Earth is rotating a little bit slower than the calculated delay with 24 hours, 60 minutes, and 60 seconds. It's a little bit slower, maybe 2 milliseconds per day slower. And this is accumulating, and after a period of time, then we have to increment the seconds counter to compensate this difference. And this is a table where you can see when these leap seconds have been added. For example, here in this year, they added 2 leap seconds, and then from here, 1 leap seconds per year, here 1 milliseconds per day, a second per year, sometimes nothing. So it's not regularly. So here you can see they added 2 leap seconds in 1 year, and here 7 years without adding any leap seconds. This is because the rotation of the Earth is not constant. This is the speed of the delay between the perfect seconds counter and the rotation of the Earth. Here, plus minus 0 milliseconds, that will be exactly 24 hours times 60 minutes times 60 seconds per day. And this shall be 86,400 seconds. But, as I said before, the Earth is rotating a little bit slower, 1 to 2 milliseconds slower than this perfect time. And then the next problem is, you can see it's not a constant. Sometimes it's faster, sometimes it's slower, and every day is changing. And this is the average over 1 year, and from year to year is different. And then this is the time difference from this perfect hours counting to the real rotation of the Earth. As you can see at these points here, I hope you can see the points. These are the points where we are adding leap seconds to stay synchronous with the rotation of the Earth to the stars and to the sun. Okay, now how do we count the time inside of the operating system Rhodos, for example? Our time unit is nanoseconds. And then when we want to express a time delay or time point, then we need some constants to say, for example, 3 seconds, 3 days, 3 weeks, 3 milliseconds, or whenever you need. Then you have to multiply. For example, we say T0 equals T10 hours. And then we have these constants. And this constant is for nanoseconds, 1. For microseconds is 1000 times 1. For milliseconds is 1000 times microseconds, and this was 1000, so 1 million. And so we go for seconds, 1 billion nanoseconds, and then minutes 60 times as much, hours another 60 times, days 24, and weeks 7 times. And this is the end of this computation, because beyond weeks, it's not regularity. The months, sometimes they are longer, sometimes they are shorter. So if we want to use regularity time, then we end with weeks. And this is exactly the same in many systems. For example, GPS, they are counting weeks and seconds of the week. Okay, and this is how it works. We have the boot time, the time where we have started the computer, and we have the beginning of time in our epoch. And this beginning of time in our epoch is Earth's 1st of January, year 2000, at time 00 UTC. Okay, and then at any time we start the computer, and from there we begin counting our own birth time. That is what we call now. So now begins from 0 and it's moving to the front. But if we want to know what is this time relative to the calendar or relative to the UTC, then we have to add this delay from here to here, and this is what we call the UTC delta time. Or we can say that is the time point when we have started the computer and begin counting with now. Approximately that is up to now 400 milliseconds. That is the time from here to here in year 2021. Okay, and then we have this time. If we add now plus delta time, we have UTC. But here, UTC, we have a problem. In UTC, we are incrementing or adding these leap seconds to stay synchronous with the Earth rotation. But for many operations, for example, computing of orbit or light time, then we don't shall use increment these leap seconds. Therefore, we have to subtract this again. So from here, we shall know how many leap seconds we have incremented in this UTC, and then we add this to the UTC, and then we have this time without leap seconds. For example, for your GPS time, or time, that is the atom clock, which is used for reference for many very precise applications. Okay, now we know how to count the time. We are working with seconds, and then we have the questions. In the computer, how shall we represent this time? We have two options. For example, we can use floating point or double for seconds. So we are counting seconds, point, and then below point we have the fractions of seconds, which can be low to nanoseconds. This is one option. Another option is to use integers. And in this integer, we can count seconds, but that will be too coarse. We need to make it finer, so we can count milliseconds, microseconds, or nanoseconds. We took the decision to count nanoseconds, and then it's very fine. But then we have a problem. We have sometimes an overflow. And maybe you remember, if we had here an integer with only 32 bits, we can count from 0 to 4 billions. And 4 billions nanoseconds is 4 seconds. So if we will use here a 32 bits variable, then we will have a time overflow every 4 seconds. If we are working with a computer, with a machine, for example, a cyclic system, and this cyclic system will never be longer than 4 seconds, then we can use this method, only 32 bits here. But we are counting the time from boot time until the end, until we turn the computer off. And this is much, much longer than 4 seconds. This is what we hope. Therefore, we use 64 bits. If you have a computer, then you can compute how long it will take until we have an overflow if we are counting nanoseconds with 64 bits. I'm going to tell you, it's about 150 years. So after 150 years, we will have an overflow, and this machine is not going to work properly anymore. But I assume no machine which we can build now can run for 150 years. So for those, is this not a problem nowadays? Okay, and now let's compare. Shall I count integer nanoseconds or shall I use floating point? To use floating point is not a good idea. I have an example of an accident because they were using floating point. And this was this rocket system. And the task of this rocket system was to protect soldiers from enemy rockets. So they have a radar systems and they can see if an enemy rocket is flying to the camp. And then they compute the position where to intersect the enemy rocket. Then they start a rocket here and then shall collide at the one position away from the camp. Okay, but they make a mistake. The people who make this program, they were using a floating point. And they're using the time 10 times per second. They are using the time plus 0.1. And the problem is there is no exact binary representation for 0.1 seconds or whenever you want. So this is only an approximation. In reality, it's 0.1, 0.0000015, and then something more. So if we are accumulating this every 10 times per second, then we are accumulating this error 10 times per second. And in this case, after 8 hours, they have a very big time difference. I think it was about 2 seconds time difference between the real clock and what they were counting here. So between this system and the radar systems, they were programmed by different people. So the time was already different. And then the consequence was, in the computations, they make a mistake of 2 seconds, and these rockets are flying with Mach 3. This is 3 times the speed of sound. And 2 seconds for t times the speed of sound is about 3 meters difference. So the rockets didn't collide. They was not able to intersect the enemy rocket. And then the enemy rocket hit the camp and they killed 50 soldiers because of this mistake, counting the time using floating point and with something which has no exact binary representation. You can have something here which has exact binary representation, for example, 0.5 or 0.25, then it will be okay. But in this case, it will not work. Okay, now I would like to remind you the classification of real-time tasks. Do you remember? We said we have tasks without time requirements and timed tasks. Tasks which have timed requirements. The tasks which have no timing requirements, they are ongoing tasks. They are running without time constraints. If they conclude today, it's good. If they conclude tomorrow, it's good. No problem. So they get CPU time only if nothing else, no other operation, no other task with higher priority are requiring the CPU. Okay, then we have the timing task. Maybe you remember when we were talking about time windows, we have 2 types. We have time sensitive and time critical systems. Time sensitive are soft real time and time critical systems are hard real time. So do you remember, to be outside of the window in time critical means you have an accident. Here it's only getting worse, but you have no accident. Okay, and then we have these 2 methods, and these 2 can be classified in other 2. Both of them can be periodic task, or they can be aperiodic task. The periodic task will repeat every period of time. And the aperiodic task, they come, execute, and conclude. And we don't know when they are going to be executed again. Here, with the periodic, if we know the length of the period, then we know when this task will be activated again. Here, it comes, it goes. It comes, it goes, and we can say no prediction when it will come again. Talking about only aperiodic tasks, we have 2 types. The sporadic task, they are reactive tasks. They are a reaction to an external event, a signal. From outside, we get a signal, and then we have a reaction to this signal. And if we don't know when this signal is going to come, for example, when the operator is going to move the mouse, or when the operator is going to press a key, or turn something on, turn something off, or if you have a network, you don't know when a message is coming, when the next byte is going to come, Or if something is flying, you don't know when it's going to be detected by radar or something like this. So you cannot predict. They are triggered from outside, and they are event-triggered systems. We have another type of aperiodic systems, and they are what we call spontaneous. And spontaneous is something like a time countdown timer. So here in the system, we find a condition when we know field side, we have to react. For example, the example I said before, when lowering the landing gear of the aeroplane, you would like to know in 10 seconds it's already down and low or not. If not, please send a warning. Or turning off the transmitter of the satellite. Do you remember these examples? This is this case. So an internal task can activate another task, and a spontaneous task will be executed for a time period, then concludes. Okay, and now let's see, in a system typically we have a mix of all of this together. We have aperiodic, we have ongoing, and then we have sporadic and spontaneous tasks, all running on the same computer. And then we have to take care which are more important, which shall have higher priority when getting the CPU, and which can wait. Of course, we can see this time critical, they shall have higher priority. In a time critical task requires the CPU, then it shall get the CPU and get processing time. Next priority shall be time sensitive. So if no time critical is running and a time sensitive needs the CPU time, then it will get the CPU time. And the last priority are the ongoing tasks. So only if no time critical and no time sensitive task requires CPU time, then we can activate the ongoing task, and they are going to perform some operations as long as no timed task requires the CPU. Okay, and now let's talk about this classification. First, let's talk about timing plan. The best thing is if you don't have timing collisions. I said before, this is going to get the CPU time only if no time critical task is running at this time point. But if you have these collisions, then it can be dangerous because this will have to wait, and maybe you will get bad results because it's going to miss its deadline. So you shall do something like a timing analysis. On this timing analysis, you have a timing line, and here you write when every task shall start and how long you consider it will take. And this is a cycle. For example, the cycle begins here. This is in the middle of the cycle, and here we are repeating the cycle, and here will be here again. And then you can see if there are no collisions, then everything is okay. We don't need priorities. But in this case, you can see a small part, they have a collisions. And these two applications. They require the CPU at the same time. And it will not work. One will be suspended, and then the other will get the CPU, depending which is more important. This is already a bad situation. So when making this time analysis, we shall consider these situations and avoid these timing collisions. And then if we do it perfectly, then the priority will never be used. Okay. And now let's talk about these three types of task: periodic, then sporadic, and spontaneous. Okay, I said before, the periodic task had a period, and they will repeat in a cyclic way. Important is, of course, the length, the computation time of the task shall be shorter than the period. Else, if it goes beyond its own period, then we have a problem. Then we cannot conclude on time. And something important is, this period can be different from task to task. It is a problem. It makes the timing analysis much more difficult if you have a system with different cycle times. So I recommend to use the same cycle time for all tasks. For example, in a satellite to do everything 2 times per second, in a rocket to do everything in 10 times per second, or something like this. But try to use always the same period, so it will be easier to make the timing analysis. And even worse, different tasks might have different periods, and you can change the period dynamically. So according to the operations, tasks shall run faster or slower. And if you do that, it's possible. The operating system which we are using, Rhodos, allow you to change the period. But if you do that, then you cannot do any timing analysis anymore. And for sure, someday you are going to have collisions. Okay. Another important thing is this periodic task begins when you start the computer, the system, and typically they stay running until the end, until you turn the computer off or the control systems. Okay. The next time was the aperiodic, sporadic task. I said before, the sporadic is a reaction to an external interrupt, to external signal. The problem here is if we want to make a timing analysis, we cannot, because we do not know when is going to come this external signal. It comes from outside of the system. The only thing we can do is make an estimation how often it can be, how speed the operator can press keys or move the mouse, and then make a worst case analysis. How many time do we have to keep free in this period to execute this sporadic task, which we cannot predict? We can only say, this is the worst case. We expect to come 100 of these signals per second. And each processing of these signals needs maybe 1 millisecond. Then we have to left 100 milliseconds in every second free to handle these sporadic tasks. Okay. And I said before, sporadic tasks we cannot predict. They come from outside. The next type of task is the spontaneous task. The spontaneous task, do you remember? They are started, triggered from inside, and they come down and then they terminate. For example, what I said before, after 30 minutes of operations, turn the transmitter of the satellite off, or in an aeroplane, after 10 seconds of lowering when the pilot wants to lower the landing gear, check if the landing gear is down and locked, else report an error. Okay, and those are the examples of these different types of tasks. And the last are the tasks without time requirements, ongoing. For example, looking for updates. They are not important, so only if the CPU has nothing to do, then we can look for updates. By the way, in satellites, we don't do that. Other things, for example, memory check. Other check hardware configurations. So every time the CPU has nothing to do, no other task, then we can activate one of these tasks, which is going to go to all memory and see if we have bits corrupted or data errors or something like this. Okay, and with this, we conclude. And this was the topic real time. Thank you very much.